Our first awardee for medicine, and you may come here if you please, because you're on the stage, is Dr. Philipp Scherer. He is professor and director of the Touchstone Diabetes Center at UT Southwestern Medical Center in Dallas. Dr. Scherer received his doctorate from the University of Basel in Switzerland and did his postdoc at MIT in 1997. After staying in cold country of Northeast, finally after 10 years, he decided to pursue his excellent work at UT Southwestern in 2007. I will let him tell us about his work. Dr. Scherer?
Thank you. It's a great honor to be chosen. I would like to thank the committee for all their hard work. It is a particular privilege to be chosen for this kind of honor in the state of Texas, where there is so much raw talent out there in biomedical research. So as such, I feel very humbled to be here today and present some of the very recent work, actually, that we are currently up to in our effort to better understand another type of energy storage, the energy storage that we actually have in our adipose tissue. So as such, I would like to highlight just a few of the critical ideas that we have developed over the last couple of years. If I manage to advance the slide. Am I using the wrong one here?
Yeah, big green.
It's the big green button that, oh, there we go. So adipose tissue is, of course, on our mind. It's on our mind all the time. I've chosen two covers here. This is the cover from a week and a half ago from the New York Times magazine. Do we have to be superhuman to lose weight? Adipose tissue center stage in that particular area. If you look at last Sunday's New York Times, on the cover again, obesity with the young and surgical procedures to get around that. So clearly, as a result, we associate an excess of adipose tissue very frequently with a lot of negative events with respect to the health. We know that an excess of adipose tissue correlates very well with an increased incidence of insulin resistance, diabetes, cancer, and many other things. But what we don't appreciate quite as much, that if we go to the opposite end of the spectrum in the context of lipoatrophy or lipodystrophy, where our fat is very limited, the amount that we have, or it's distributed in the wrong places, we start to appreciate that we really need our adipose tissue, because a lack of adipose tissue is also associated with very severe forms of insulin resistance. Our main objects of affection are these cells here. They come in many different sizes, but they always have the same shape, the adipocyte. They can be skinny, as we've seen on the left, and as we gain weight, we fill these adipocytes up with excess energy, mostly in the form of triglycerides. But rather than just serving as a triglyceride storage compartment, we've also appreciated that these adipocytes communicate with the rest of the system in many, many different ways. And basically, every single cell system-wide is directly or indirectly under the influence of these adipocytes, under their lipid influence, under their hormonal influence, and as such, these interactions have been well worked out for the last couple of years. Again, the main purpose that we embrace in the context of the adipocyte, it's their role to store excess energy, so energy metabolism is a key role. But the last 10 to 15 years have also highlighted a very intimate connection between a dysregulation of energy metabolism and an increase in inflammation. And at the same time, an increase in inflammation will actually cause some degree of dysregulation at the level of energy metabolism. I will also spend a little bit of time telling you about one or two proteins that may actually play a role in this connection of increased risk for cancer incidence and development and progression in the context of excess adipose tissue and highlight some of the factors that might explain that phenomenon. Now, I stole this slide from a colleague of mine at UT Southwestern who conventionally uses it to highlight the differences between males and females. However, I'm going to use this actually to highlight the difference between what we knew about 25 years ago about fat cells and what we know today. It used to be a very, very simple cell. Its purpose was to store triglycerides, and up on demand, it would release triglycerides in the form of lipolysis and supply those triglycerides to the system. Now we know that this is a cell that has many bells and whistles that can be regulated in many different ways and affect the system in very profound ways. And this is just one example of an overview that we've tried to create a couple of months ago in terms of the kind of events that take place as we go from a healthy, lean adipose pad, fat pad, to a dysregulated, unhealthy fat pad that we see here, and how that affects many of the other tissues that are directly subject to regulation by fat cells. If we boil this down to a much simpler scheme, we could basically argue that as we develop dysfunctional fat tissue, we have an increased migration of a lot of immune cells, particularly macrophages, and that cross-reaction, that interaction between the infiltrating macrophages and the surrounding adipocytes is responsible in many ways for the type of dysregulation that we can observe under those conditions. And actually, when you look carefully in your fat, as we gain weight, we actually do notice that these macrophages surround dead fat cells, and they start to gobble up these excess lipid droplets that stay behind as we lose some of these fat cells, and they start to look like foam cells in an atherosclerotic plaque in your vessels as they increase their lipid content. And you see these lipid vesicles over here. This is a macrophage. This is the dead fat cell here, and you see these lipid droplets that surround these cells. Now, what my lab has been trying to figure out for many years is to define how can we actually keep adipose tissue healthy while it expands, because it has to expand since we expose ourselves continually to an excess caloric intake. What are the critical factors that are responsible for maintaining proper health of adipose tissue? And some of the critical dysregulated steps are highlighted here. If you look at the non-functional fat pad, and we'll define that a little better, what that means, a non-functional fat pad, you'll see that fat pads that don't work properly because they are hypoxic, they don't have enough oxygen supply, they have a high degree of extracellular matrix content, so they are fibrotic, they lack proper vascularization, and because they are very active secretory cell, they also activate a process called the unfolded protein response, which is a stress response within the secretory pathway. And all of these things ultimately result in some degree of inflammation, and it's that kind of inflammation that really ultimately triggers the insulin resistance. There is a progression in this process as we go from lean functional to dysfunctional and obese, and you can see here that we propose that one of the earliest events that take place is actually as the fat cell grows and stores increased levels of lipids, and it almost instantaneously becomes hypoxic, because the vascularization cannot keep up with the demand. One of the things that cells do when they become hypoxic is they induce a critical transcription factor, which is a master regulator of hypoxia, attempting to avoid and bypass the hypoxia by building up increased vessel density, blood vessel density, and that factor is called HIF-1 alpha. And HIF-1 alpha, in the case of the adipocyte, causes that increased fibrosis. It fails to induce the angiogenesis, but it causes the increased fibrosis, leading to increased death of these adipocytes, and as a result, we have secondary to that the inflammation. Now, we can take advantage of that when we look now with this HIF-1 alpha action as it leads to fibrosis and unsuccessfully tries to induce the angiogenesis. Pharmacologically, we can actually inhibit that particular step. And we can learn actually an awful lot from our colleagues in the cancer field that have actually learned to manipulate this factor very effectively in the context of tumors, where HIF-1 alpha also plays a major role. And what you can see here is that there is indeed a HIF-1 alpha program induced, similar to the type of genes that a tumor cell induces in these dysfunctional adipocytes. Glucose transporter, extracellular matrix components are induced. And in fact, when we do this either in vitro here, in tissue culture, or in vivo, we can actually inhibit that transcriptional program that is being induced. The question for us is, of course, the ultimate test is if we inhibit now this factor HIF-1 alpha pharmacologically, can we actually improve the metabolic health, in this particular case of the mouse? And it turns out, yes, indeed, HIF-1 alpha inhibition, whether we do it pharmacologically, as we show it here, or genetically, will actually lead to a very significant improvement in metabolism. It will reduce the weight gain in the context of putting these mice on a high-fat diet. And when we use classical tests of metabolic functions, such as what are the baseline glucose levels in the fasted state, well, they normalize. What is the rate of glucose disposal as we feed these animals glucose gavage? The animals actually are dramatically improved in their glucose disposal, all of which is not really affecting the food intake of these animals. So they have an increased energy expenditure. We don't just make them sick and they lose weight. They're actually very happy mice on that treatment, but they do improve their metabolism very significantly. The other help we can provide to these cells is not only to prevent the fibrosis, but we could actually stimulate what HIF-1 alpha fails to properly do. We can actually now, for instance, genetically supply an excess vasculature by overexpressing, in this particular case, a key factor for angiogenesis, VEGF. And indeed, it's a little hard to see, but that sky in the dark here that you see, the increased number of lights, is basically a reflection of an increased density of blood vessels that we can generate now by inducing VEGF genetically in these mice. And lo and behold, if we provide that extra vasculature, we do build a healthier fat pad, and we do improve the overall health, the metabolic health of these animals, as judged by an oral glucose tolerance test as well. And in parallel, they also dispose of a lipid challenge much more effectively. And that's, again, a reflection of healthy adipose tissue under those conditions. One of the things we see over and over again when we improve the overall health of adipose tissue, other tissues actually benefit from that as well. If you look, for instance, at the liver after a high-fat diet, in the control animals, the liver becomes very lipid-laden, has a lot of triglycerides that you see here on the left. The transgenic livers with healthy fat actually have a much better-looking appearance with very limited lipid accumulation and much improved insulin sensitivity at the level of the hepatocyte as well. So when we look at this pyramid of evil here, so in the context of diabetes, the one thing we can always notice is that the first cell that gives, the first cell that cannot keep up with the metabolic dysregulation in the system, tends to be the beta cell. That's the insulin-producing cell in the pancreas, and it has to work extremely hard because it has to overcome a very high degree of insulin resistance in the system. And that insulin resistance has a number of reasons, but one of the reasons why a cell becomes insulin resistant is because it starts to accumulate lipids in inappropriate places, and we refer to that as ectopic lipid deposition. And when that happens, we can conclude that this only happens once our adipose tissue, which is the main organ that's specialized in storing triglycerides, once that adipose tissue is no longer properly functional to fulfill its main role, these lipids start to spill over into these other tissues and start to induce an awful lot of damage. And as a consequence, we can actually see this in model after model after model again. The metabolic flexibility of the adipocyte in terms of its ability to accommodate and release excess energy effectively has a profound impact on other tissues in the system as well. in this very recent work with my late colleague Dick Anderson at UT Southwestern, we've looked at a mouse that lacks a specific protein in adipocytes called caveolin-1, which is an important scaffold protein for various signaling molecules, for complex reasons that results in a dysfunction of the mitochondria in these adipocytes. And secondary to that, we have an increased release of free fatty acids from these adipocytes, ultimately triggering dysfunction in other tissues, including the liver in this particular case as well, where the liver starts to become quote-unquote metabolically inflexible because it runs exclusively on carbohydrates at this point. So it overproduces glucose over and over again and cannot really effectively adjust. We can measure this metabolic inflexibility when we measure a parameter called respiratory quotient, where we can actually tell whether a mouse, or for that matter a patient, preferentially burns fat or preferentially burns carbohydrates. And the ability to go from one to the other, in the fasted state we want to burn fat because that's when we tap into our reserves, whereas in the fed state we want to burn carbohydrates. That is again governed to some extent as an initial step by the adipocyte that can effectively release fatty acids on the times when we need it and re-esterify that. And the ability to go back and forth is actually very important. The dysregulation of that process at the level of the adipocyte similarly affects the ability of the liver to do so as we go from fasting to feeding. The liver completely has to change its metabolic program and actually get away from the carbohydrate production during the fast over to assimilation of excess calories. And that, again, is a reflection of the metabolic flexibility. And we've recently found, actually, not just in the liver, but particularly in the liver, a molecule called XBP1S turns out to be a very important component in the adjustment from one state to the other. If you have a metabolically challenged mouse, a diabetic mouse, for instance, we notice that this key factor, which is supposed to fluctuate off and on in order to adjust to altered metabolic states, that factor is constantly on, and because it can no longer cycle now, leads to a very high degree of dysregulation at the level of the liver again, with the original cause actually going back to the adipocyte again and its inability to adjust properly. So we want to keep a healthy adipocyte basically at all costs. Now, I showed you an example in these caveolin-1 knockout mice where the mitochondrial function was negatively affected. We've also found ways of manipulating mitochondrial function positively in our white adipose tissue by, again, genetically adding, in this particular case, an excess of a protein called meitonine. And I want you to meet Frida here. Frida is actually the world's fattest mouse at present, and she and her sisters actually have massively expanded their adipose, their subcutaneous adipose tissue, and that mouse is actually almost 130 grams here. Now, it makes you wonder, if your tax dollars at work here, you're creating the world's fattest mouse. Well, what can we do with that type of information? It turns out these mice are incredibly valuable, actually, because when we study these mice a little bit more closely metabolically, we find that despite the fact that these mice are morbidly obese, their metabolic health is the same as a 25-gram mouse on a normal chow diet. They're absolutely perfect. They have clean livers, they're highly insulin sensitive, as you can see. Their glucose levels are perfectly normal. So it is an example by which we have managed in this particular case to expand the fat mass in a very healthy way, highly vascularized, very little inflammation, and accommodate a massive and overcome a massive intake of food that these particular mice are prone to, and they neutralize these extra calories very effectively by putting them into the subcutaneous fat. So, and again, as a result, these mice have wonderful looking fat with little inflammation, and their livers on the top right-hand side, you can see it from afar, completely devoid of these nasty lipid droplets that you conventionally see in the context of high-fat diet feeding. So we definitely managed to expand these in a healthy way. Is there a parallel in the clinic? Absolutely. Just because you may have a BMI of 40, it doesn't necessarily mean that you're a type 2 diabetic. Just because you have a BMI of 25 doesn't mean that you're not a diabetic. So individuals that may put an excess weight on very quickly, and they do that in a healthy way, actually represent, admittedly, a small percentage of all obese individuals, but those are the ones which actually maintain excellent metabolic health despite an excess of BMI, and they will be the clinical equivalent of the mouse that I've just shown you. Now, why don't we then, I've shown you that adding VEGF, for instance, to the system can actually have great benefits. So why don't we just do this pharmacologically? We could inject VEGF and actually improve the health of our adipose tissue. Well, it turns out there are many examples of things where this does not go very well, because anything we do to improve the health of our adipose tissue is actually also aiding the tumor growth. And many pharmacological interventions that have been tested over the years failed, not because they weren't effective in improving fat health, but they actually were ineffective because they also induced an increased rate of tumor growth. Now, I want to introduce you very briefly to just a brand new protein, which we termed endotrophin, that may actually form a link between the established connection of increased body mass index and increased tumor incidence and decreased prognosis in terms of obese individuals. Many cancers are affected by that: breast cancer, colon cancer, pancreatic cancer, and particularly endometrial cancer. And we suspect that this increased cancer incidence is a reflection of something negative that the adipocyte releases that will actually support tumor growth under those conditions. And it turns out a couple of different factors do that, and one of the factors that we are very excited about these days, we termed endotrophin. This is a factor that you won't find anywhere out there yet. At least I hope you don't, because if you do, that means we got scooped. But we termed this cleavage fragment of one of the abundant collagens in the context of adipose tissue, that little red cleavage fragment at the end. We called it endotrophin, and it turns out this is a factor that is highly induced in adipose tissue that's surrounded by tumors. It has a very high affinity for the tumors, as you can see with this brown stain here, and it makes tumor cells extremely comfortable. It assists, actually, if we express it in an isolated manner, it enhances tumor growth. These are mammary tumors that we watch here. It increases the rate of metastases. It causes actually a high degree of fibrosis, so it induces this extracellular matrix program. It enhances angiogenesis. So it does all the things that a fat cell can do to enhance how comfortable a tumor is. And it enhances also the macrophage infiltration. So we are excited about this because we do know that this is a factor that we overexpress in the obese state. And certainly in the context of tumors, it makes these tumors incredibly more comfortable in their environment. It increases their tumor growth rate. And we're excited about therapeutic possibilities by neutralizing these factors and thereby restricting these obesity-associated tumor growth phenomena that we observe under those conditions. But it's not a factor that's exclusively apparent in terms of its potent action in the context of a tumor challenge. It is actually a protein that's expressed on the normal conditions in our adipose tissue and actually is responsible for some of the dysregulation that we see under those conditions. It does increase the fibrosis of normal adipose tissue as well, and as such, it will actually cause some degree of metabolic dysregulation as well. So this is a brand new factor that we are currently working on, that we hope we can actually get a better handle on with neutralizing antibodies and use those as therapeutic agents. Now, with all that negative talk about adipose tissue and all the evil things that an adipocyte does, I want to leave you with a positive note as I'm approaching my last minute. and briefly mention this protein adiponectin that we've identified about 15 years ago by now. This is a wonderful protein that actually behaves in a completely different way from all the other fat-derived molecules, because the more fat we have, the less of it is in circulation. And it does a lot of wonderful things in terms of its effects system-wide. We actually use this protein now as a biomarker to gauge the relative health of our adipose tissue, and the higher the levels in circulation, the better off we are in many different aspects. In fact, when we make mice that have an excess of this protein, again, these mice become very fat, but they retain metabolic health, because in this particular case, they're very well vascularized subcutaneous fat preserves their insulin sensitivity. It is a long list, about almost 10,000 publications on this protein by now. There's a long list of things that have been attributed to this protein, all of which are actually very positive. It improves insulin sensitivity, it's pro-survival, it's anti-inflammatory. And it turns out that this particular protein, its main action is actually on a particularly nasty group of lipids that we tend to accumulate when we overeat in excess, and those are the sphingolipids. So rather than either burning these lipids or storing them in our subcutaneous fat, we can also generate a small population of these so-called ceramides. And these ceramides tend to cause a lot of nasty metabolic side effects. They actually cause insulin resistance directly in target cells. And what we found about a year and a half ago is that adiponectin is very effective at scavenging, at degrading these excess ceramides in a number of different tissues. In this particular case, we look at liver. And they also generate the degradation product, the sphingosine 1-phosphates, which are also a rather esoteric group of lipids that are very beneficial, on the other hand, for our metabolic health. So it does do so by an activation of its receptors. Those are enzymes that degrade ceramides, and as a result, you have a lot of beneficial effects, not just on cardiac myocytes, not just on the liver, but last but not least, also on our insulin-producing beta cells that are actually well preserved in the context of high-fat diet exposures once we provide an excess of adiponectin, and they tend to display a much better rate of survival in this intricate crosstalk between the fat tissue and our insulin-producing beta cells in the pancreas. So this is just a small component of this adipoinsular axis that I myself and also some of my other colleagues are currently working on very intensely. Us in the context of adiponectin, Dr. Unger, whom we meet tonight, has a very interesting set of studies in the context of leptin. Bottom line is, we want to be nice to our fat cells. We want to keep them happy, because when they're happy, they do their job best. They will remain insulin sensitive. They are anti-lipotoxic, because they will neutralize these excess lipids, and they will preserve our metabolic flexibility, not just in adipose tissue, but also in other tissues. And they do this on the basis of maintaining their own insulin sensitivity, as well as the release of many key factors into the system. So with that, I would like to conclude and thank many people. Particularly, I've been blessed with many very talented collaborators in my lab over the years. I am surrounded by a wonderful group of colleagues at UT Southwestern, three of which I want to mention specifically because they have been very key to our day-to-day operation: Jay Horton, Joel Elmquist, and Roger Unger. But then also the funding agencies, the JDRF and the American Diabetes Association, the NIH. But most importantly, I am heading the Touchstone Diabetes Center, and I would like to very much acknowledge my gratitude to the Touchstone family who've supported the center for many years and who in fact actually are here today in the audience as well. With that, I would like to conclude. Thank you very much.
We have time for a few questions. Well, while they're thinking about questions, something occurred to me. and I can't say I know anything about the subject, but you said something, there are 10,000 publications on a subject area?
They're not ours only,
No,
unfortunately,
no.
but in the context of adiponectin, there are, in fact, you do a PubMed search and you'll come up with about 10,000 publications.
Wow. Well, I hope you have 10,000 of your own.
Yeah.
Question.
Phil, that was an outstanding lecture. Congratulations on this award. Well deserved. Question. So we just finished the human transcriptome of obese adipocytes isolated from visceral or sub-Q fat versus lean in humans, the adipocytes themselves. And we actually saw an increase in collagen 6, but of course we don't know the endotrophin story. So what I wanted to ask you though was, you talked about healthy fat. So healthy fat, presumably you want the collagen 6 or endotrophin because that helps with the vascularization. But on the other hand, it has negative effects on tumors. So how are we going to balance the healthy fat but keep tumors from growing?
Well, as you're aware, the pharmacology is very complex there, and the industry really struggles with coming up with an effective treatment because if you do one, you always do the other one as well, at least for the most part. So everything except perhaps metformin that has not been implicated. In fact, it's been anti-tumorigenic. But everything else, the PPO gamma agonists, the dual agonists, they've all died basically because of that. So I guess until we find a way to either increase our energy expenditure or reduce our energy intake, which unfortunately will be very hard because we have to hit the brain with that, I'm actually quite pessimistic that there is an effective, that there will be an effective way of doing both.
Because if you cut off collagen 6, if you stop that, then you might have back to unhealthy fat.
Well, if you cut off collagen 6, you can actually reduce the fibrosis. You actually will have reduced mechanical stability of your fat, which is a bad thing, but you will have improved insulin sensitivity.
Oh, okay.
You
so
do.
it
We
works
know that
the other
already.
way.
Yes.
Okay, thank you.
Hi, Phil.
Hi.
Great work.
Thank you.
Hope you shared that money well with your colleagues at UT Southwestern.
Champagne.
I have a question that's related somewhat to the previous one and to your talk as well. Two former winners of this award got it for angiogenesis inhibitors, which they suggested would be, and it's been suggested not only by them, by others, would be very effective at preventing diabetes by preventing the differentiation and proliferation of fat cells. I was wondering if you might comment on that because your data and several others suggest that that would not be a desirable thing to do.
Well, thanks, Dave, for the question. So I only told you part one and I skipped part two of the story. It's actually complex but very interesting. If you face a lean fat pad that is expanding by exposing the mouse to a high-fat diet and you supply extra VEGF, you will actually have a healthy expansion of adipose tissue. If you have a pre-existing dysfunctional fat pad and you cut off the circulation to that dysfunctional fat pad, you're going to have a lot of dead fat cells which used to be dysfunctional, and it turns out that we are actually better off with the dead fat cells than having these dysfunctional fat cells around. So we've reproduced these studies. If you have an OB mouse and we neutralize VEGF in an OB mouse, the mouse will actually get metabolically better. But the difference is, are we going from lean to obese and in the process providing the necessary infrastructure? We will maintain metabolic health. If we have already a diseased model and cut off circulation, we actually make the model better by reducing vascularization and killing off, literally, fat cells in the process that would otherwise be highly inflammatory and negative for the system.
Yeah, so let me jump up to the very practical level, the human level. And I did read both of those New York Times articles and found them very discouraging and depressing. So my question is, I guess there has been a movement in America for accepting larger body sizes and not always trying to diet and the like. And where do you make the distinction about healthy weight and body frame and metabolic rate, some of which is genetically driven, and where people should always be striving for exercise and leaner body size?
Well, the one thing I really want you to away with here is I was not implying, this was not an endorsement for obesity. This was a proof of principle that if you expand your fat pad in a healthy way, you can maintain metabolic health. In the clinical setting, it's only very few that actually can do this based on their genetic makeup, that they gain weight very effectively, but they will keep their metabolic health at a very high level in that process. But for the vast majority, the correlations still stand that increased BMI will predispose you to a dramatically increased risk for type 2 diabetes, will predispose you to increased risk for cardiovascular disease. So this was merely a proof of principle that once we neutralize these lipids, tuck them away into metabolically healthy fat pad, we can maintain metabolic health. But most of us are not predisposed to do that, and we actually fail to maintain our metabolic health in fat, and as a consequence, are prone to diabetes.
Very good. Thank you very much.